Next topic in the same line is astronomical telescope, but this one is not the normal adjustment. See, I have already drawn this ray diagram, so it will be easier for you guys to understand how it is drawn. First of all, what is the again magnifying power of astronomical telescope? In normal adjustment, we did this definition that it is the ratio of angles subtended at the eye by final image to that of object when both final image and object are at infinity. This time, final image, I'll again come to this point how this final image is formed, but this time the definition goes like this change, that this time it is the ratio of angles subtended at the eye by the final image and that of object when when final image is at least distance of distinct vision and the object is at infinity. Alright, this will be the minor change. First of all, our object is at infinity, from where rays which are coming parallel. Okay, we have taken these three rays which are coming parallel. I have already told you how to draw this ray diagram in astronomical telescope in normal adjustment, that first of all extend the central line which is passing from the optical center. See, the logic behind is a ray which passes through, which is coming from infinity and passes through optical center, is supposed to meet at focus, but this time the ray is not coming parallel to principal axis, so it is not going to meet exactly at the focus, but it will meet somewhere in the focal plane. So this point is the focal length of objective lens, which is this one, and this is the focal length of objective lens. So what happens, first of all guys, just extend this central line. See, you have taken these three parallel lines and stop these lines right here, okay, from where your objective lens is. Then only stretch this line or extend this one line wherever you want to make the image, stop that at that point, and then join this point and this point with the image. So this will be your image which is getting formed from the objective. Usually we take AB sign notation for objective, A dash B dash for the first lens, first image. So this is your A dash and B dash, right? Now what happened in normal adjustment, the same point was the focal length of eyepiece as well, due to which what happened, when an object is placed at the focal length of any lens, the image is going to get formed at infinity. One ray which is going parallel to principal axis will pass through the focus, this is the focal length of eyepiece, and the other ray which passes through the optical center C2, this was C1, is going to go straight. So in that case these two rays were getting parallel because the object was at focus of eyepiece, because focal length of objective and eyepiece were coinciding, and so these two rays were also going at infinity and their projection was also going towards infinity. So we got the final image as well as at the infinity, right? But here the focal length of eyepiece is up to this point. That means the image of the first lens which is serving as an object for the second lens, this object, that is A dash B dash, is within the focal length area or focal length distance of the eyepiece, due to which what will happen, a virtual image is going to get formed, virtual and erect. So this image which is virtual and erect for this object is getting formed at some point, right? So what is this is how you draw the ray diagram. First of all you extended the central ray up to this point, then you joined this point and this point with wherever you want your diagram or your image to be, right? Then after that you made the line parallel from the principal axis and stop it right here, don't pass it through the focal length first mark this line which is going from the optical center of second lens and stretch it on the other side or on the dotted version wherever you want your final image to be. For example, I want final image height to be this one, so I'll be making this line first, and then after making image I'll be joining dotted version here and I'll stretch it. Wherever it crosses the principal axis, there I'll mark the focal length. So what we are doing, we are just trying to solve the complications involved in making such kind of ray diagrams, because otherwise if you will take the measurements and then what will happen, your final image might go out of the boundary of the paper. So to avoid that complication, we are doing it other way around, right? Now to derive the equation, the formula for magnifying power of compound astronomical telescope, this is, remember this point that this is not in normal adjustment, right? So how do we start? Magnifying power is ratio of angles subtended at the eye by final image, which is, this is your observer. So this angle must be what? Final image is this one, beta. So this angle goes for beta. And object is at infinity. So what vertically opposed angle, this angle would be alpha, right? If you want me to write the angles in different colors so that you can see it every time, this is beta, all right? Now the angles are more visible. Now beta upon alpha, which will be equal to tan beta over tan alpha, because when angles are small, sin theta tends to theta and tan theta also tends to theta. Tan beta over tan alpha. I'll be using more of the blank space here, so keep tracking the next point. Tan beta would be, I can either take this height over this base with this angle, or I can go for this height and this base, though the idea would be same. We are taking this one because it can cancel out with when we'll be taking tan alpha. So magnification, which is tan beta over tan alpha, in case of tan beta I am writing a dash b dash upon a dash c2. This is a dash b dash upon a dash c2 over tan alpha. Tan alpha is height, this height upon this base, right? So this is a dash b dash upon a dash c1. A dash b dash upon a dash c1. Now this will cancel out and you are left with, this goes up, magnification is equal to a dash c1 upon a dash c2, right? Now what is a dash c1? Though this length is the image distance for the objective lens, but this is also the focal length of objective lens, because the rays which are coming from infinity are meeting at the focal plane. So this a dash c1 is the focal length of objective lens, number one. Number two, a dash c2, this length is basically the object distance. Here this length is the object distance for eyepiece. So this is UE, which is negative in sign, right? So I can actually write this thing like this: m is equal to f naught multiplied by minus 1 upon UE. The equation still remains same. We had f naught upon minus UE. I have just separated it with a bracket. Why? I'll just tell you. F naught multiplied by minus 1 upon UE. Why I have done that? See, we have this formula 1 upon V minus 1 over U is equal to 1 over F, right? I am writing E for eyepiece everywhere. I want this term minus 1 upon UE. So minus 1 upon UE is equal to, take this term this side, you will get 1 upon FE minus 1 upon VE. If I take 1 minus 1 upon UE, if I take 1 upon FE common out, what will I get? This term will become 1 minus FE will be on numerator side VE. How did I get this conclusion? Multiply this term inside the bracket. What will you get? 1 upon FE into 1 is this term. 1 upon FE into this term, FE gets cancelled out, you will be left with 1 upon VE, which is this term. So this is the idea how you take this common out. So minus 1 upon UE can be replaced by this whole term. So here where we have minus 1 upon UE, here you will be writing magnification is equal to f naught multiplied by this term into 1 upon FE. 1 upon FE is like this, 1 minus FE over VE, right? So this is your final answer for magnifying power of astronomical telescope. And when this distance VE is on that side, like left side, and if you replace it by least distance of distinct vision, so you can replace this term by minus D. D is the least distance of distinct vision, and in that case you will get 1 plus FE over D. So this is the formulation for magnifying power of astronomical telescope.